A warm welcome, my dear friends, my dear students. Very good morning, good afternoon, good evening to all of you. This is the DADM 1 course, which is Data Analysis and Decision Making under the NPTEL MOOC series set of courses. And this course is for 12 weeks, which is for 60 lectures. Total content hours would be 30. And as you know that in each week we have 5 course classes, each class being for half an hour, and we are in the 7th week. So, today is the 34th lecture with another 2 lectures of each of half an hour. We should wrap up the 7th week set of classes. And my name is Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we were discussing about something with a very simple example about cupola theory, and based on that we said that, or the extreme value distributions, and we were discussing that in the extreme value distributions what we are interested is to find out. I will not go into the properties and definitions with full vigor. So, given a data set we want to find out the extremes. So, the example where they can be used. So, if you remember that I did discuss that cupola, or which is a linkage function to give 2 random variables, it is basically utilized to find out the relationship of 2 random variables at the extremes. Now, covariances are nice linkage function, nice dependence function between 2 random variables, but they are linear in nature. So, if in the extremes it may become non-linear. Say for example, some financial crisis occurs, like say for example the one in 2008. So, it had a devastating effect on the banking sector, on the overall economy, and obviously if I want to find out the risk level pertaining to the devastating financial crisis which happened in USA, I want to find out what effect would it have on, say for example, on oil prices, or say for example on the financial sector in India. Obviously in India was shielded because of its own policies, it was able to overcome the extent of losses to a greater extent. But say for example a country like Greece, country like other European countries, they were affected devastatingly. So, in that case we will try to basically consider that the relationship between the effect and at the extremes shocks which happen with huge amount of intensity, but the actual probability of occurring of those shocks occurring is very rare events considered. Then we basically use extreme value distribution. Extreme value distribution is also used for flows of fluids. There we want to understand that as the speed increases or as the velocity increases, what effect it will have on the as a pressure front, on the force front, and so on and so forth. Now, whenever we are considering extreme value distribution, what we actually do in very simple cases. So, consider the data set is given, and as I was demonstrating, I will demonstrate again. As the data set is given, we will take the minimum value. Now, the minimum value is basically for a set of data set. So, I will try to basically portray that using in this this PPT slide only. So, let me add few blank slides and proceed. Let me add few blank slides. So, it will be easier. I thought I would not, but let me basically go through it in detail. Now, consider the let me use the red color. So, you have a data set with values of x1, x2, x3, and it goes on. See for example, take xt, the t can be anything 1000, 2000, whatever. Now, I want to find out the extreme value of this in distribution. Consider it is extreme value, consider it is stock prices for the very simple and case. So, technically we have the, so what we are doing is that we have the prices. So, price is given per day. So, it is by, and for any stock P1, P2 till PT. Based on that we find out the return. So, return it would not come up here, but it basically would start from the second one. R1 is equal to ln of P2 by P1. Similarly, you will have some R2, continue this way, you will have basically the values as given. So, there would be one less return. So, when so this would be t, say for example, coming up to t minus 1, even though they would technically should be written one step up. Now, these values, the returns which I have are extreme value, in the sense I will show it to you. There are data points, actually they have been utilized. So, consider if it is a positive distribution, so it will be like this. It is a negative distribution, it will be like this, which is basically for the positive, this is for the negative, this is the losses, this is the gains. Now, what we do? We take a block of them, now use a different color. So, we take a block. It does not mean only x3, it can be set of values. So, in the first block you have x1, x2, so on and so forth. Then consider you are taking till say 30 for the example. So, it is 31 to 60, 61 to 90, and it goes on. Now, what I do is that I take the minimum of this, I take the minimum of this, I take the minimum of this. So, I take the minimum of this, and once I have the minimum, so consider the minimum I will denote as x. This is in a bracket 1, even though they are actually that is the formula for the ordered pairs, ordered from the ascending or descending, but I will just use it for simplicity. So, this is the first one, this is for the second, and so on and so forth. Now, once I have these minimums, technically it means that I have taken a small sample of whatever the size is from an actual population which consists of the minimum distribution, which is an extreme value. Consider either minimum is this one, not the maximum. Now, I do a sort of bootstrapping. Bootstrapping is basically, consider you have a high boot where there are a lot of shoe eyes, the lace to tie up, you need a lot of tying up to do, those old fashioned boots. So, in bootstrapping it basically means you are tightening up from the lowest level, and as you go up you basically do it in such a way that you are trying to find out the best estimate in the concept of bootstrapping. So, in bootstrapping technically we take a small sample and increase the size. So, the increase in the size, there are many different methods which we do. Increase the size in such a way that the actual sample size now explodes, lot of actual readings are there. So, the underlying probability of any sample size remains the same. So, say for example, in a small sample you have 1, 2, 3, 4 and 5 is 2 times. So, the technically of 6 values, 1 occurs 1 by 6th, 2 occurs 1 by 6th, 3 occurs 1 by 6th, 4 occurs 1 by 6th, 5 occurs 2 by 6. Now, you blow it up in such a way that you basically add up 1, 2, 3, 4 and 2 number of 5s many number of times proportionally. So, if you add them proportionally, then say for example, you add them 10 number of times. Now, the total number of readings would now be basically 60. So, now in this case 1 would occur 10 by 60, which is 1/6, which remains as the same relative frequency of the chance of the probability as it was earlier. In the same case number 2 would occur 10 by 60 again, which is 1/6, 3 would occur again 10 by 60, which is 1/6, 4 will occur again 10 by 60, which is 1/6, and 5 will occur 20 by 6 divided by 60, which is 2/6. So, concatenation in this way or increase in this way basically would give you a replication of the population which you are trying to emulate. Now, with this data you basically jumble it up. Jumble it up means basically shuffle it, like you have a set of values inside a box and you basically jumble it up such that the probability when you pick which number you will pick up is absolutely random. So, when you pick up those numbers and keep repeating it time after time, then the actual sample mean in the long run would be exactly equal to the population mean. To give a simple example, what I mean by not by the concept of bootstrapping, but picking up the sample characteristics of the sample averages time after time would basically replicate the population average. Consider you have a this example I think I have repeated in the initial 3-4 lectures of this course. Consider you have a coin and it is an unbiased coin, the probabilities are half and half for a head and a tail. But say for example, you toss it 100 number of times for the first case and you get 45 heads and 55 tails. So, obviously the relative frequency of a head and a tail is 45 by 100 which is 0.45 and 55 by 100 which is 0.55 respectively. Now, keep repeating it, do it again 100 times, find out the heads, find out the tails, note it down. Again do 100 times, keep and do it infinite number of times. Now, the proportions of the heads you will get will obviously differ. In one case it can be 0.45 in the first case, then it can be 0.46, then in another case it can be 0.60, so on and so forth, any value is possible. Now, if you find out the actual averages of this average, that is the total number of heads divided by the total number of tosses in the long run, then obviously that will be equal to 0.5 which is actually the probability. In the same way, what we are considering is that we can basically pick up these observations time after time, find out the sample mean such that the average of the sample mean in the actual case considering the unbiased and consistency property in the long run should be exactly equal to the population mean. So, obviously you will use these concepts in order to basically bootstrap and find out that considering extreme value distributions are to be plotted, you can do that. Now, this example which I gave for tossing a coin would also be true for the case when you are basically rolling a die. You are playing a game of Ludo and considering the it is an unbiased die and the probabilities are 1/6, 1/6, 1/6 for each 1, 2, 3, then 1/6 for 4, 1/6 for 5, 1/6 for 6. Now, when you roll it 200 number of times, the number of chances of getting either a 1 or 2 or 3 or 4 or 5 or 6 actually would definitely be different than the respective probability which is 1 by 6. Now, you keep repeating it many number of times, infinite number of times and find out the proportions of number of heads, proportions number of sorry not heads, number 1, proportions of number of 2, proportions of number of 3, proportions of number of 4, proportions of number of 5, proportions of number of 6, and in the long run you will find out the probabilities for all of them numbers appearing is 1 by 6. So, you will basically use this concept in the very simple case of bootstrapping. Obviously, there are many complicated methods, but generally bootstrapping would work accordingly. Now, in the case of the minimum, as I told that you take many of the minimums and basically concatenate it, concatenate means increase the size proportionally, jumbled it up and pick up a set of samples or observations and find out some mean and continue doing picking up these samples with replacement, remember, such that in the long run average of the sample means is equal to the population mean. Similarly, you can do the same thing considering the concept of unbiasedness and consistency for the variance and all these things. And from them you can find out the parameters of the distribution which I did tell is the location parameter, shape parameter and the scale parameter which we generally denote by alpha, beta and gamma. Now, the question would be, can I do it for the maximum? Yes, you can again do the same thing for the maximum for the EVDs, but in that case remember that you will basically take the maximum value for each subsets, this 30 which I am mentioning, in each case take the maxima. So, I will take the maxima, repeat it, find out the maxima, take it at one go, concatenate it, do bootstrapping, find out the means and find out the mean of the overall population. And again you can do for the standard deviations and on these things. So, these are blanks as I will just skip. Okay. Now, this what I mentioned, I will do it for, I will show you some actual results which I had done for few of the MBA and the MTech studies. So, I will just show it to you. We will show the univariate extreme value distribution. I am taking the univariate case because if you remember trying to find out for the multivariate case, ranking system may change because if you rank the first values, now obviously it does not mean that you are ranking the second set of random variables or vice versa. So, we will show the univariate extreme value case using the positive values of returns. So, the returns are given as I mentioned log to the base e of the price of today divided by the price of yesterday. So, that will be the returns of yesterday. Similarly, price for tomorrow divided the price of today will give me the returns for today, and I will proceed accordingly. We do it for the indices of 4 countries, for doing Nikkei, which is for Japan, Nifty. So, obviously in India you have the NSE and the BSE. I am taking the National Stock Exchange, which is for India. FTSE, which is Financial Times index, which is for United Kingdom or UK, and the KOSPI, which is for basically for South Korea. We take the data from 2003 to 2012. So, what we do is that we take the end of the day closing price for this index. Index is a conglomeration of stocks depending on whatever number of stocks which are there. So, once you do that, you and actually each year on an average you will have about 240 data points. I did mention that because considering the Saturdays, holidays, holiday and the national holidays. So, based on that you have the closing price of that day, and technically you obviously people would intuitively think that the closing price for today would be the opening price by tomorrow. Technically that should be the case, but that is not the case, that besides the point. So, you have the closing price based on the closing price of 240 per year. So, you will take basically 2003 to 2012, and those number of some days which you have, you will find out the corresponding returns by the formula. So, it will be example log of price on 2nd of January 2003 divide the price of 1st January 2003, and continue till the last value would be log of the 31st December 2012 divided by the price of 30th December 2012. So, once you do that, I have the returns. Now, one thing remember, these I am not doing bootstrapping, not doing the so-called, I didn't mention one thing. So, taking the blocks and doing the bootstrapping is known as block bootstrapping. So, they can be blocks on the windows which can be overlapping, non-overlapping. In my other concept, when I am taking the blocks of x1 to x30, x31 to x60, x61 to x90. So, those blocks are non-overlapping. You can take overlapping block bootstrap also. But in this case, because the data size is very large, you can take the returns as such, or you can definitely do the block bootstrapping with overlapping time periods or without overlapping time periods, and then plot the returns of these 4 different indices. Now, as I mentioned, for these values which you get, this expected value after you do either the bootstrapping, do not do the bootstrapping, from this mean value, variance, skewness, kurtosis, which are the first respect to the first moment, respect to the second moment, respect to the third moment, respect to the fourth moment, that is mean, variance, skewness, kurtosis. You can find out the parameters of the distribution. Now, if you remember the parameters concept, for a uniform distribution discrete case it is A and B, for a normal distribution is mu and sigma, for exponential it could be A lambda or only lambda, for Poisson it can be only lambda. So, all the, and for a binomial it will be n and p. So, all those are the parameters, just to recap. Now, technically for any distribution the parameters are in general given as alpha, beta, gamma. So, these I consider as mu, sigma and eta. So, they are basically the shape parameter, scale parameter and the location parameter, and for the EVD's values, these for this for the stocks which we take generally the for the Indian one, for the FTSE, for the KOSPI and all these things, we find out the parameters of the shape, scale and location as 0.092, 0.0075, 0.0158, that is mu, sigma and eta. Similarly, for the second case is 0.14745, 0.0084, 0.0169. For the third case, which is FTSE, it is 0.1475, 0.0068, 0.0118, and for the last one, which is the KOSPI, it is 0.1571, 0.0074, 0.1610, 0.0163, which is basically the values which I have are for the Nikkei, and then the Nifty, then you have the FTSE, and if I lastly you have the KOSPI. Considering the returns as negative, so we are considering the returns technically as negative or positive, whatever you can consider, minimum or the maximum. We can also calculate the values of, we can do that, find out the values of mu, sigma and eta. So, in this negative case we will take the minimum, in the positive case we will take the maximum. So, we are basically taking the maximum value, hence we are taking the positive returns. So, the graph which we are going to show is not for the minimum or the negative one. So, this is for the Nifty. So, this is the multivariate extreme value distribution example, but only considering the univariate extreme case. So, if you remember, I will just draw it, that we had drawn the graph like this. So, here it is, and these are actual values. So, obviously, these are true. This is for the Nifty, and I basically draw the PDF, and these values are given, returns are given on the x axis starting from -1 to 0 plus 0.8. Similarly, if I do it for the Nikkei, this is the PDF of Nikkei, then again the values are, this comes out to be quite nice as an extreme value distribution for the univariate case for the positive returns. And obviously, if I take the negative returns just for the information, it will be like that, you can definitely double check. Then I do it for the FTSE, for the UK market, again returns are like this, these are positive returns. And finally, when I do it for the KOSPI, which is for the South Korean market, again the values are like this. So, similarly you can do it for the negative one. I am just giving it an one-to-one correspondence so you can understand. Now, we will basically consider the simple methods of trying to basically find out how you do it for the ML estimate of the parameters related to the multivariate normal distribution only. So, consider that x's are the x is basically a matrix of size n cross p, and I am basically noting. So, obviously, there is a notational difference here. I am noting it down as the first value 1 comma 1 is x11, and I go along the first row till the value which is x1 comma p. So, these are basically the first values for the p number of random variables. So, technically you could have considered x p cross n also, but that is just a nomenclature I am following. Second row would be x2 comma 1 till the last value which is x2 comma p. So, in that case it will be the values for the second reading for all the random variables 1 to p, and similarly the last row is x n comma 1 till next n comma p, which denotes the nth reading for the random variable starting from 1 to p. So, if you one needs to estimate the parameters, then obviously the total number of parameters to be estimated would be half into p plus 1 depending on the mean values and the standard deviation you are going to calculate. Now, I am not digressing, just a point. So, when we will go into the multiple linear regression also, we will consider the same concept time and again, that given the multivariate normal distribution, we will try to basically estimate the betas and proceed accordingly. So, there obviously x can be given as p cross n. So, this is a bold, remember. So, that is why I am highlighting it. This is a matrix. And similarly, when you consider y later on for the multiple linear regression, y would be a vector of size n cross 1. So, those nomenclature of multiplying the rows and columns should be considered accordingly, so that there is no dimensionality problem. Now, in general, if you remember, if I have not discussed that and I didn't go into details. So, basically in the multiple linear regression models or in multivariate statistical models, the method to basically estimate the parameters would be almost the same, the conceptual method would almost be the same as we had done in the univariate case. So, in the univariate case, if you remember, what we have done, we have considered the maximum likelihood estimation problem. So, in the maximum likelihood estimation problem of the method of moments. So, consider the maximum likelihood estimation methods. You took that, consider the parameters are unknown, you pick up a sample and the realized values are x1 to xn, only one case, univariate. Now, you found out the corresponding probability of x1 occurring, x2 occurring, x3 occurring to xn occurring. Then I want to basically find out the corresponding probability. So, I would basically try to find out their IID, remember. So, hence I multiply, find out the corresponding probability of occurrence of all of them one at a time, and you are basically picking up with replacement. So, it would not matter whether x2 is different or x1 is different from each other. We find out the maximum occurrences of this probability given that alpha and beta are such values which will maximize them. But considering that it log if equation is a monotone increasing function, we convert into a logarithmic function and differentiate with respect to alpha, beta, gamma, whichever they are. So, obviously, they would be the corresponding parameters which are scale, shape and location. Put it to 0, find out the linear set of simultaneous equation if possible, solve it and find out the alpha hat, beta hat, gamma hat. And obviously, if they are not, then use different type of iteration methods, Runge-Kutta method, then Newton-Raphson method. In many of the cases, you have to use the different type of heuristic method, genetic algorithm, artificial immune system, you have to use the ant colony optimization, all these things could be used. So, we would basically be using those methods also, but they are from the theoretical point. So, let us consider the case of the multiple linear multiple normal distribution such that we formulate the log likelihood functions accordingly. So, the log likelihood functions would be exactly the same. So, in the first part you will basically have no parameters with respect to x or the with respect to the parameters. Here is basically something to do with the variance covariance matrix, and this is the part which is basically to do the third part with respect to the differences. This you remember in the simple case. So, differentiate with respect to alpha, beta, gamma, whichever the parameters, put it to 0 and solve it. So, I will continue discussing more that in the 35th class of this NPTEL MOOC series of DADM. So, with this I end this class and have a nice day and thank you very much for your attention.